My name is Kendall Brown, and I'm the acting Deputy Project Manager at Marshall Space Flight Center for the Altair Lunar Lander. Prior to January of this year, I was also the propulsion subsystem lead and responsible for the design and development planning of the propulsion systems for the Altair Lunar Lander.
My name is Tony Kim. I'm the Deep Throttling Technology Development Manager. I've been working this technology work since 2005.
My name is Gregg Jones. I work at Marshall Space Flight Center, the Combustion Devices Group, and I'm the team lead in that group.
In the lunar lander propulsion systems, and particularly the descent propulsion system, there's a requirement in order to have a soft touchdown on the lunar surface that the descent main engine throttle. With the design studies and the alternative propulsion systems, we identified that some configurations would require throttling to approximately 12% power level. Given that combustion instabilities can occur when throttling a liquid rocket propulsion system, there is a risk that we would not be able to develop the technologies required to achieve the required throttle rate and the required throttle range in order to meet the development schedule for the Altair Lunar Lander. So the risk that we were trying to evaluate and trying to mitigate was, given that undesirable and unacceptable low-frequency combustion instabilities, also known as Chug, can occur with a high-performance liquid rocket propulsion engine below about 20% power level. And given that in some of the vehicle designs we might require an engine that throttles to 12% power level, there's a risk that we will not be able to solve the issues and develop an engine to meet the requirements within the available cost and to meet the required schedule date. The Altair Lunar Lander has a more difficult propulsion system design challenge than the Apollo Lunar Lander propulsion systems. That's because the Altair, the future propulsion systems, have to do more due to the mission requirements. With the architecture within the Constellation launch program, the Altair Lunar Lander has to perform the lunar orbit insertion burn. In the Apollo program, the Apollo service module propulsion system performed that maneuver instead of the descent propulsion system. We're also planning to have a lot more robust lunar exploration campaign, and thus having more crew on the surface, carrying more cargo to the surface in order to develop a more robust exploration program. So that makes the lunar lander heavier, and it makes it larger because we have to carry more propellant to perform all of those mission functions. When the Altair Lunar Lander project began in April 2007, we started studying to understand where the optimum performance, because there's a trade-off between the thrust level of the descent main engine when you perform the high impulse lunar orbit insertion burn and then the initial part of the lunar descent burn before you need the throttling before you need the engine to throttle to obtain the soft shutdown and landing on the surface. There's a variety of options that we evaluated, including single engine versus multiple engine configurations. So we performed an analysis to understand the effects of these multiple engines. Adding multiple engines can add mass. And there's also an optimum thrust level that, due to the way the gravity losses occur during the mission, and from this chart, we see that the optimum thrust level is past about 30,000 pounds of thrust. Using existing liquid rocket engine technologies and making assumptions about how to achieve throttling, we were limited to about 18,600 pounds of thrust. From this curve, we can see that that provides an approximate penalty of about 400 pounds. So that would be about the weight of an astronaut with his spacesuit, that extra on the vehicle associated with not having the optimum engine. But having additional thrust requires additional throttle range. Then when we look at multiple engines, if we go to, say, 4 engines, and we want to have a reliability improvement by being able to land with an engine inoperable, then we have to operate the engine at 75% power during a nominal mission and throttle down to the low throttle point in order to land, but then if we have an engine out, then we have to throttle up to maintain the same thrust in order to land at the designated location. So using the thrust and the engine configurations in either single engine or multiple engine configurations, we're able to bound the possible required throttle ranges by looking at the required maximum thrust and the required minimum thrust. We obtain the required minimum thrust by looking at the dry mass of the lander at the point of touchdown, assuming that we have used all of the usable propellant. Well, at that point, just before final touchdown, we need to be able to descent. We don't want the crew to be sitting there hovering and then have a sudden drop. So that defines a minimum thrust at about 75% of the final landed mass. Using that as a minimum thrust, and then the maximum thrust as being the obtained from the performance trade-off between number of engines and thrust level versus gravity losses, that provides a throttle range. So using the engine that we thought was going to be a low technology development of about 18,600 pounds thrust, that would require a throttle range of about 3.3 to 1, or a minimum throttle of 30%. It's interesting to note that during the Apollo program, the Apollo lunar lander maximum, the lowest power level was about 25% power. So the thrust of that engine is in line with what Apollo actually performed. However, the Apollo lunar lander also had a requirement that when they initially started the engine, they would start to 10% power level. And that 10% power level would be used to get the inertial navigation platforms and the star trackers on the spacecraft lined up so that they performed the correct maneuver.
The deep throttling technology for a LOX hydrogen pump-fed cryogenic engine is enabling technology for the Altair project. Because deep throttling, going from 100% power to 10% power, was required by the project, we needed to demonstrate that this was possible. And to do that, we used a few different approaches. To attack this deep throttling engine approach, we utilized a couple contractors initially. One was with Pratt & Whitney Rocketdyne with the RL-10 engine, and it is the Common Extensible Cryogenic Engine. We call it CC. And we modified the RL-10 minimally with a high delta P injector and some valving to be able to throttle the engine from 100% to 10%. We also attacked this problem with Northrop Grumman, utilizing the variable area injector that is the pintle injector for throttling from 100% to 10%. We later approached this problem with Aerojet because they came up with a very innovative approach and demonstrated on a subscale injector, and we got Aerojet involved in attacking this problem by utilizing their platelet manufacturing technology that allowed very intricate fuel flow paths to attack this deep throttling problem.
One of the reasons we're really concerned about the risks involved in the Chug instabilities is that those instabilities can lead to vibrations on the vehicle, cause thrust variations that could cause us to miss our landing site, or land harder than we need to and harder than we designed to, and then could potentially kill or hurt the crew. So that's why the mitigating the Chug instabilities is important. So as we began the risk mitigation activities, and there were a couple things that had been going on from previous programs, and we had and in the DCX program in the late 90s, they had done some throttling with a high performance engine down to about 33%. We knew and we really felt that we needed to go below it, even if we didn't. Even if we were able to have a design that only needed about a 30% minimum throttle range, we wanted to be able to have margin to ensure the safety of the crew. That's why we were so concerned about this risk, and we also wanted to have the ability to use multiple engines with engine out. And if we used multiple engines in an engine out scenario, we would have to go down to a very low minimum power level of about 12%. So we needed to be able to understand the problem as we worked the risk mitigation strategy against that, against the chug instability risk. We wanted to have a multi-prong approach. We wanted to have one that kind of was a primary where we felt we had some confidence in, and that was with a fixed orifice injector using a derivative of the RL10 engine. We also knew that from the Apollo program, the pedal injector had been very successful, and it had been more successful in mitigating instabilities than a fixed orifice injector. And we were using different propellants than the Apollo program used, and that's why and pedal injector had never operated with cryogenic propellants in a throttling situation. So that gave us a couple of alternatives. There were some alternatives within the literature and within some of the knowledge of our combustion instability experts, both at NASA and within NASA's contractors, of yet a third approach. So the risk mitigation strategy included multiple design concepts, multiple ideas in case one of those didn't work. Because the CC engine, or the derivative RL10 engine, was the most mature, it was the easiest piece of hardware to get into test. So the Demo 1 program was originally intended to just demonstrate that we could reach these throttle levels. In previous programs, and the RL10 has a tremendous history of trying different things, and actually in the 60s, beginning back to 1964, there was a program where they did some throttling with an engine, and they actually tried to address some of the chug instabilities and understand chug instabilities. But because the engineers that worked that program have long since retired, a lot of that information, a lot of that knowledge has been lost. So we wanted to recreate that knowledge. And so the original idea was that it wasn't going to be a very hard problem. We first started into the Demo 1 program and realized that, and immediately towards the end of the program, encountered the chug instabilities, and then had some issues with the engine in the program, and had to come back in another cycle of testing in the Demo 1.5 program, and explored extensively the engine operational, the engine performance range in which throttling would occur, combination of mixture ratio and power level.
There was something that happened during CC that is very interesting in the fact that we did an extensive literature search on what was done in the past. The RL10 had been tested before for throttling back in the 60s, and we knew that, that was a very capable thing for us to do, but we needed to get the experience base. And there was an article that was done, a technical memo that was done back in the 1960s, and it was missing 2 pages. In the 2 pages that were missing, the discussion was insulation of the LOX manifold. And we only found that piece of paper by accident with somebody who knew that we were working on this, found it for us. And we found that in between the second test series and the third test series, when we were actively putting insulation on the injector. So it's an interesting story. If we had that piece of information at the beginning, we might have started out with the insulated injector in the first place.
As that program proceeded, we began to understand the phenomenon in greater detail, combined with the knowledge we had from literature searches and from analysis based upon the test data. That allowed us to structure the Demo 1.6 program, which included an insulated injector. That injector and that test program demonstrated that we understood the chug instability phenomenon caused by the boiling of the liquid oxygen in the oxygen manifold. That allowed us to then, because we had successfully mitigated the chug instability itself, we still had concerns with respect to how the engine could be controlled. and actually meet the throttle rates so that we were able to precision land and avoid hazards. One of the things we were trying to do with a new exploration program was that if we wanted to go land on the backside of a crater, that we could throttle up and then throttle down and essentially like a helicopter jump up and over a hill in order to land at the exact place we wanted to land to perform the mission. That requires the control system to operate very well. And with the original test setup, it was designed to very quickly and inexpensively get the hardware into test to understand the specific chug instability phenomenon. So in demo 1.7, we spent more time, and the contractor spent more time understanding the control of the engine and operating that RL10 engine in a way that had never been operated before, and proved once again that it is very successful and that we understood which of the valves on the engine were going to be the most challenging to continue working on in order to meet the reliability and the mission performance requirements. After the chug was encountered in the demo 1 and demo 1.5, that led us to believe that our initial plan of having a backup strategy for mitigating the chug instability was the right approach. So we ensured that we had some hardware that was being fabricated using the pedal injector technology from Northrop Grumman that we could then bring into hardware and test and understand how the pedal injector was going to perform just as a backup plan or as to provide alternative schemes. One of the important features of our mitigation plan was that we would have chug, have injector technologies to address the chug instability provided by multiple contractors. This would allow us to enable competition at the point where we would do a competition for the engine development program. So as we proceeded forward with the pedal injector and the pedal injector testing, we then went to a two-stage injector, which was a concept that was designed and developed by the engineers here at Marshall Space Flight Center. As this program was going on, a third industry contractor, under their own internal research and development funding, started another concept of their own and demonstrated that through their own testing program. As they showed us the data from that testing, we decided that it would be good and it would further broaden our risk mitigation approach by including that and having it at the same scale and the same operating conditions, so we could compare now 4 different injector concepts to mitigate the chug instability risk.
So there's several methods we used to reduce chug in literature. For the Altair program, we focused on 3 methods which had been tried before but hadn't been developed for this application. The 3 methods are a high delta P injector, a continuously throttling pintle, and finally a 2-stage injector. The high pressure drop injector was used on the CC program, and what it does is it has really high high pressure drop across the injection element at high power, maybe 5 to 10 times as much as a normal injector would. So if you have really high pressure at high power, when you throttle down to low power and it drops, you still have enough pressure drop to keep the combustion oscillations separated from the feed system so you can eliminate chug. The problem with that is it takes really high pressure drops to do that, twice as high as you usually have. So that's a system problem with it. So that's one method. A second method is a continuously throttling pintle injector. And what that is a piston. And as the piston moves back and forth, it uncovers area or closes off areas. So at high power, you have the areas opened up wide, low pressure drop, so the system works good at high power. At low pressure, the piston closes down, making little areas, high pressure drop, so we still prevent chug by having high pressure drop at low power. So it worked. That's the second method. That's also the method that the LMD used, the Apollo Lunar Lander engine used a throttling pintle, but was with hypergolic propellants instead of cryogenic propellants like Altair wants to use. Finally, the last method is a 2-stage injector. This is kind of a combination of the first 2 methods. It's got at high power, it's got 2 cavities you use and 2 orifices. So you have lower pressure at high power because you get 2 different ones. And when you throttle down, you close off one of the areas. So a pintle gives you infinite amounts of area. A 2-stage gives you 2 different separate areas. But it's also nice that it gives you 2 design points, so you can design for high performance at low power and at high power. So those are the three methods that we investigated with the Altair program.
First, let me talk about CC, the Common Extensible Cryogenic Engine. Initially, we had a one-year contract with options, and the first demonstration was accomplished in the first year. And what they had to accomplish was basically to show that it was possible in a LOX hydrogen cryogenic engine, a pump-fed engine, to be able to throttle from 100% to 10%. And we were able to basically accomplish that within the year, but it was at the last test that we actually accomplished this. And in the last test, what did happen was we found out that we had Chug at lower power settings. So because we learned that in the first test series, but just basically at the end, we needed more data. So we modified the contract to be able to test again and really try to understand the lower power regime so that we can quantify what Chug was doing to the engine or how it was being created. We were able to get back into the test, and we call it the Demo 1.5, the second test series, and we were able to learn more about chugging. We spent a lot of time down there at the lower power settings investigating Chug. What we did learn was that the Chug was initiated due to the fact that vapor was being created, LOX vapor was being created inside the LOX manifold, causing two-phase flow. And that was creating a boundary layer that inhibited the propellant from flowing. So with that, we went to the next test series, and that took about a year and a half to get to. But basically what we did for our third test series was we went to attack the problem. We utilized a couple different approaches to mitigate Chug, and one of them was insulating the LOX manifold so that we would isolate the heat from getting into the LOX manifold. And the other is utilizing helium injection to make the propellant consistent, compliancy of the propellant consistent so that we wouldn't have the inhibition of vapor causing the LOX not to flow as well or to actually oscillate. So on the third test series, we actively attacked the problem, and we found out that we really did understand the mechanisms of Chug, and we understood the physics of the problem. And so we basically solved the problem of Chug.
The primary lesson learned from this activity was the importance of a flight program iterating with the technology development program. Flight engine being able to define the requirements and work interactively with the technology developers to ensure that the technology developers are addressing the problems that the flight program is interested in. Another key takeaway is that the strategy we had at the beginning of this risk mitigation activity to have a primary and backup mitigation approaches was very sound. When we ran into concerns with the fixed orifice injector approach, we had the pintle injector approach, we had the two-stage injector approach that we still developed, and in some cases we spent more effort to make sure they were going to be able to get to the test program. We were able to, at the end, understand and mitigate the Chug with the fixed orifice injector. But if we had not, and it had been, we would have had a large schedule delay and cost impact if we had had to try to reach back into the beginning days of the program and bring those other design solutions forward. One of the key success stories within this risk mitigation strategy is that the combination of the government team within NASA and within NASA at multiple centers, Glenn Research Center, Marshall Space Flight Center, worked together And then they worked together with the contractors, and the contractors were very open, and everybody was on the same page trying to solve the problem.
Working with Pratt & Whitney Rocketdyne, between the contractor engineers as well as the civil servant engineers, and us developing a really cohesive team that communicated well, was critical for this technology development effort. One of the things historically is that Pratt & Whitney isn't so open with their knowledge and ideas, and that can inhibit communication. And I think what we did really well in this project is that we formed a really good trust between the contractor team and the government team, where there was a really good flow of information because of the trust that was developed, and they provided a lot more information to us freely in a way where it was noticed that we worked well together.
Another major benefit that we were able to take advantage of during this program was that the RL-10 engine hardware was available. And some of the hardware we used on that engine had actually been used during the DCX program in the late 90s. So some of those valves, and because the contractor was able to have held on to that hardware, it was available for our use. So a takeaway that I have is we need to try to protect our hardware and not just throw it in the scrap when we finish a program. As we began working with the PCAD project, we defined the requirements, and we used a document called the Customer Supplier Agreement. By documenting our flight program requirements in terms of threshold requirements and goal requirements, we were able to periodically review that document to see whether anything had changed. As our analysis on the vehicle showed that we needed only 12% throttle versus 10% throttle, the document was changed to reflect that. As we defined thrust levels and as we defined the rate of throttle, we reflected that in that document. So that document became a very good tool for allowing us to control requirements and to make sure that requirements creep didn't flow into the technology development projects and then slow them down or increase their cost or delay their schedule.
Changing budgets has been a huge challenge for this technology development effort. As I mentioned before, I had to actually stop the Pinto contract from moving forward because of lack of funds. Also for CC, we initially had a plan to spend a certain amount of money, and my budget was reduced along the way, and so there were times that we had to change direction or modify it. And those things, as well as what we learned through testing, and as well as our customer requirements, we had to be very flexible on how we approached these tests. And overall, it was a huge challenge, but it's something that we need to be able to adjust to be able to accomplish a technology development program. We have to be always in alignment with our customer needs, and so that was a challenge, but it was a challenge that worked out pretty well considering the circumstances. Testing is critical to understanding the engine. Analysis is important, but ultimately testing is what shows that it can be done. And the amount of money that we spent on CC over 5 years, we were able to get a lot done, but we had one engine and we had 4 test series over the 5-year period. And if you look back at what the testing that was done back in the 60s, they had hundreds and hundreds of tests. Over the 5 years, we had approximately 40 tests for CC. And granted, we built off of what was done back in the 60s. We were able to accomplish what we did with the 40 tests because of the fact that we had a lot more analytical tools, a lot more computing power with the new computer technology, but it was still a challenge. There was a point when we were meeting with some graybeards, and they asked about our budget. And we told them our budget, and they basically looked around and said, peanuts. And I said, okay, what do they mean by that? Were they converting 2,000 year money back to 1960s money? I don't know, but basically they were able to spend a lot more money to be able to do a lot more tests, and that's why they were able to accomplish what they did back then. But we were very challenged to do the minimal amount of testing, because testing a rocket engine costs a lot. And we accomplished what we did. We felt we were very successful, but more money for testing is necessary, in my opinion.
If you'd like more information about this activity, feel free to contact any one of us in the video or contact the Propulsion Systems Department within the Engineering Directorate at Marshall Space Flight Center.